frequency. This is the frequency that, because of the laws of nature, it wants to vibrate at. And so there it is. Now, it doesn't have to always be at its natural frequency if something outside of nature, which I don't know how to say that because everything's in nature, but you know, I'm part of nature, but watch this. If I grab this, whoop, I can do this. Whoops, I shook it off. In fact, why don't I just take it off here? But if I hook it on here, I could take my hand and shake it. I could shake it at a high frequency. I could shake it at a low frequency. And so the shaking of my hand is the frequency that it vibrates at. In other words, it doesn't vibrate at its natural frequency. Its natural frequency is what it kind of wants to do on its own. And so if my hand or a machine is not connected to it, forcing it to go at some other frequency, it has a natural frequency. These things here have a natural frequency. If I pull them back and let them go, they shake at some natural frequency. That is the laws of nature, which in this case would be the inertia or the mass that they are up here, the force of gravity and the stiffness of those metal rods that are holding them. All of those would come in together, and you can see that this one has a lower frequency than this one, and this one is somewhere in between. They each have their own natural frequency. This one has a natural frequency, and as we talked about, it's a combination of the stiffness of the spring and the mass I'm hooking to it. And so for a given spring and a given mass, they have a natural frequency. Now, let me switch to 100 grams, but a different 100 grams. The reason why is this 100 grams has a tighter fit, and so I don't think it will come off. At least I hope it won't come off. So if I hold it with my hand here, and I pull it down and I let it go, that's its natural frequency. But what if my support hand were to shake? Well, I could shake my support hand at a high frequency. And see, notice it would shake at that high frequency. It's not at its natural frequency. It shakes at the frequency of my hand, the driving force. That's what I would put over here in this definition. That's this when a periodic force is applied to it. So I'm applying a periodic force, and it would of course shake at that periodic force. But this definition is something quite interesting happens. What happens if that periodic force is the same as the natural frequency? So I'll show you again. This is its natural frequency. This is my hand at a periodic force that is at a frequency higher than it. I could even do my hand at a periodic frequency that is at a lower frequency. And you'll see the weight go up and down with that frequency. But when my hand is at the same frequency as the natural frequency, watch this. Now, maybe I'll get it started so I can kind of tell what the natural frequency is. And I move my hand at the same rate. I don't have to move it much. But if I get that just right, it will really oscillate, and it'll have huge amplitudes of oscillations. Now you can see why I wanted to hook it up there. And so this is what this is trying to say, that under these perfect conditions, where the applied force, the periodic force, is at the same value as its natural frequency, you'll get these amazingly large frequencies. And that can be good or bad. It depends what you're trying to design or to build. For example, if you want something to shake, then after you build it, take a measurement of its stiffness. You can even push on it or let the wind blow it and see what it naturally shakes at. And then you know that if you apply a frequency at that, it'll really start shaking. Now, if you don't want it to shake by a lot, then don't shake it at that value. You can see that really well with this little machine. We call it our earthquake machine. I borrowed it from our engineering classroom because this one has a ground that is then hooked to a little motor here. I'll turn the motor by hand here at first, and so maybe you can see the platform move as I move it back and forth. Let me just get the rollers about situated. And so as I turn the motor, this turns this rod, which shakes the table. Now, keep in mind that we have, this is supposed to represent 3 buildings, a single-story building, a 2-story building, and a 3-story building. They have a natural frequency. If I, let me start at a low speed. Turn it on, and of course I have no speed right now. And if I give it just a little bit of speed, okay, right out there, the motor kind of turns, the ground turns, and the buildings go back and forth at the same rate of this periodic frequency that I'm driving it at. But this frequency is so low, although now it's starting to get high. Maybe I'll put it right there. Now, I'm getting close to the natural frequency of the 3-story building. Oh, good. That looks way better. But they all just go back at this rate. But something quite amazingly happens. This is the resonance. When the ground shakes, so here, at just the right frequency. There it is. See how much that 3-story building shakes, and in this case probably would fall down if a building shook that much. And so during this earthquake with the frequency at this rate, the 3-story building falls down, but the 2-story and the 1-story don't. But watch this. As I increase the rate of this motor, and I increase the rate that it shakes, I can get this. I can get the 2-story building to shake a lot. Whereas the 3-story and the 1-story don't shake a lot. See if I can get a little better. Right there. And so that 2-story building is shaking like crazy, and in this case would fall down, because I am matching then the periodic force with its natural ones. And so this 2-story one falls down, but the 1-story and the 3-story stay up fine. And then, of course, you probably noticed that the 1-story building had the highest frequency. So let me go to a higher frequency. There we go. And my roller's not real good for this. But that single-story building is shaking like crazy, and the other 2 are not. Kind of loud when I get to those higher frequencies here. But that's this whole idea of resonance here. Another good example is maybe you've heard like what they call maybe the ultimate test. What is the ultimate test of an opera singer's, he or she's quality of singing? Well, can they break a wine glass? And a naive response to that is, oh, wow, they must be loud. No, it's not so much they are loud, although that's part of it too. But did you see that they have a natural response? If you take a wine glass, if you've ever hit the side of a wine glass, you will hear it ring. The molecules of glass are vibrating back and forth. And it's that ringing that is telling you its natural frequency. And so the real key here is for the singer to be able to copy that pitch, that tone. They got to hear it, ding, and they got to be exactly the same. Because you saw that even when I shake the ground at a high frequency, it did very little to this building. At the right frequency, it would demolish this one, but not this one. And so it wasn't how much it was shaking that was important, although that's part of it. So it's not how loud the opera singer is, although that's part of it. More importantly is how, what frequency they are. Can they exactly match that natural frequency to break a wine glass? That's really an amazing one here. Well, we better keep going. I've probably taken way too long looking here up at the clock on these first bits of it. But that's the first half of the chapter. Now, the second half of this chapter continues on with this. And for you to kind of see that, I set up a second table. Let me go ahead and wheel this table out of the way. And I think that's far enough to be off camera. And let me just bring the second table into play. And it looks like my time is about to run out on me, and just as well. But at least I'll kind of introduce the second half of this chapter, now that we've spent all this time talking about these oscillations, because the second half, let me just kind of grab my notes here, is to then say, well, what is a wave? And you probably noticed that a few times in this discussion, I have kind of talked about waves, although I was really trying to introduce you to oscillations, because the wave is the next natural step. I would say a wave is a vibration that moves. I might also say it's a flow of energy. The best way I can really kind of describe a wave really is to show you. And so these things are called wave machines because they're little metal rods, which, I don't know, without the zoom, if you can kind of see, they are individual rods that can move up and down. But they're not independent of each other. These rods, oh, and I just damaged another one. This one's getting kind of old. That's why I brought the second one out. But I like these longer ones. You'll see why. But they're a little bit damaged with age. But the rods can move up and down, but they are connected to each other. So if I make one oscillate, because it's connected to the next one oscillates. And then as that second one oscillates, it makes the third one, and then the fourth one, and then the fifth one. But it gives all of its energy to the next one, so the original ones stop oscillating. Watch. Here's just the best way I can describe a wave, is just watch it. I make a little hump and let go. You see, the first one then gives its energy to the second one, which gives its energy to the third one, which gives it to the fourth one, and then the fifth one, and then the sixth one, and the seventh one, and the eighth one. And so there's this flow of energy. It's what I would call a vibration that moves. I hope you see here on the camera that it actually looks like something is moving. But I want to emphasize, there is no material that is moving. There was nothing here that moved all the way down to here. Well, what happened is it started here and went to there. And when I say it, what I mean is their energy. There is a flow of the energy, not the material itself. The oscillations move. The oscillations are the energy. And so you can see why we did not do this with our mechanics. You can see why we call these mechanical waves. I mean, they do have something to do with mechanics, but they are not like way back in chapter 7 where we said, okay, take a baseball and throw it across the room. And as the baseball went across the room, we would say the energy went over to there. But we would also say the material went over to there. That's our mechanics. Ooh, the material does not move. And so some very interesting and different physics can take place when you have a movement of just energy, a flow of energy without the flow of matter. Now, I'll show you the other wave machine. This is kind of a fun one to see first, but with the smaller rods, if you remember back in chapter 8, the rotational inertia, where the the rotational inertia depends upon how far the mass is out. In fact, there was some really good questions on the test. I'm thinking of one with that wheel, the disc, where it was spinning around. And so as it spins around, it said the two wheels have the same mass, and one of them's thinner, so the mass is further out, and you were supposed to include, hey, further out means more rotational inertia. So that's what I'm trying to point out here. These rods are longer, they have more rotational inertia, they would be harder to move back and forth, so they would have a different rate of oscillations than these guys. And you see that right here. If I just take this strip and lift up the first one and let it go, you'll hopefully see the first one starts the next one, which starts the next one. But they do it at a much quicker rate. And in some sense, kind of fun to watch those because they go so quick. And none of them are broken, unlike this one. This one, once I get started, there's a couple broken on each ends over the years here. But that's our whole idea of waves. Now, waves don't just have to do this kind of motion. They could also do this type of motion. And maybe this will be a good stopping point, and we'll get into the definitions tomorrow's lecture. But this machine back here, if I push on this rod, the rods are mounted vertically, and then they push each other across here. So again, I would call this a wave, because once I make a disturbance here, once I make an oscillation, they send it on down here. And so this disturbs that one all the way down. So there is a flow of energy without a flow of the material. Well, like I said, good place to stop here for today. This is our first half of the chapter. We'll pick this up tomorrow with our first lecture, and then of course keep moving along here. So I'll call it quits, although I'm going to have to run to the back of the room to actually turn the camera off. So I will see you then on Tuesday, tomorrow. Bye now.